sun. We're going to talk about the sun. Do you like it? Not that sun. No, I'm kidding. But we are going to talk about this sun. This sun is a pretty amazing thing. This sun is the one and only reason that we are alive. It gives us the energy to stay alive, right? We can study from hundreds of millions of miles away. We can study the sun and its atmosphere pretty intently. And so that's what we're going to do. We're going to kind of dive into what events, because the sun is not just this white dot in the sky that we see, right? It is fascinating, and it is full of energy and excitement and all sorts of different things. So let's dive in. First, we got to talk about these dark things that we see on the surface of the sun. We see these things called sunspots. They're darkening parts of the corona, or the outer shell of the sun, where we could see that it's much cooler. So scientists can, through different technology, figure out what the surface of the sun, truly the temperature is, and likewise, if there's a sunspot, what that might be as well. So we see that these dark areas in the photosphere, or the corona, is cooler than its surroundings and has a stronger magnetic field. It's kind of like a storm on the face of the sun. Okay, it forms when magnetic fields reduce their energy in energy transfer zones. Weaker currents means darker sunspots. Okay, up to 3,000 degrees Celsius cooler than the surrounding regions. 3,000 degrees Celsius, I think that's really difficult for us to even comprehend. 3,000 degrees Celsius, that's 1,000 more degrees than the flame of a lighter is, right? The flame of a lighter is under 2,000 degrees Celsius. We're talking about a lot of difference in temperature, okay? Sunspots appear in groups. Typically, they're large, and can have the diameter of more than 100,000 kilometers. Earth's diameter is roughly 13,000 kilometers, right? So these can be massively larger than the Earth. Let's take a look at a couple. Right, so here's an image that NASA took with a filter. They've got all sorts, if you Google sun images, you will see all sorts of different color suns. Well, it's not that we have different color suns, it's that people take them with different filters on that give you different images. So this is one with a filter on it that allows us to see these dark spots on the surface very prominently. Okay? Like I said, these spaces are very active. Okay? Not that the rest of the sun isn't active, but these are extremely active spots, sunspots. And here is one kind of zoomed up close, almost looks like an eye. This surface area, this surface temperature is much cooler, up to 3,000 degrees cooler than the surrounding area. Same thing here. Right in the middle, that can be up to 3,000 degrees cooler than the surrounding area of the sun. Okay, so that's one activity that we see on the sun. We see these in cycles. All right, sunspots happen approximately every 11 years. We see a spike, and then we see a downward turn, and then we see a spike, and then we see a downward turn. And we can go back centuries to identify this cycle. Cycles begin when the number of sunspots are very low and begin to increase. They appear in groups about midway between the sun's equator and the poles. The number of sunspots increase over a few years until the peak of about 100, and then it slowly dissipates or disappears. We're on the uptrend, or the top side of an 11-year cycle. So pretty soon we're going to see this a graph where we begin to go down in our 11-year cycle. So that's pretty cool. So we go all the way back to January of 2000, before you were born, I bet. And we see a peak with 125 all the way up to 175 number of sunspots, and then we go way down to 09, right? And then 09, 10, 11, 12, we see a climb, okay? And we're going to see a climb again up until about 14, maybe 15, and we'll start to see this. The red line is projection down, okay? Same thing here. Here's 1995. Low spots, high spots here in the 2000, 2005, all the way to here's 2009 where it was really low, and now we're right about here where it's beginning to curve over the crest of the graph. Okay, and then the last graph here, we go all the way back to the 1600s. Right, 1600s we see very minimal back here. So if we start really at the 1700s, we see very distinct cycles. Right, and roughly about every 11 years we see a sunspot cycle where it's up for a period of time and then it's down for a period of time. So those are sunspots. The next few items that we're going to talk about are what are called solar ejections. Now these include prominences, solar flares, and coronal mass ejections, also known as CMEs. That's what coronal mass ejections is. And I'm sure you've seen on the news that term, CMEs. Okay, so let's take a look at NASA catching a glimpse of one of these solar ejections. It's all of these in one, a prominence, a solar flare, and a coronal mass ejection. So let's take a look. We have dramatic music as well. That's happening right here. And it's just a loop going over and over and over, slowed down. But right here is, we see a huge burst of energy, an explosion from inside the sun. And these are just different filters, like I said. Here it comes. And then you see all of this material being sucked back to the sun. Here's another picture. Right, all of this material is being sucked back because the sun is extremely gravitational, has a massive amount of gravity, so it's grabbing that material that's going outward and pulling it back in. And it's full of magnetism as well. So this is just one example out of hundreds that we could see with regards to a mass ejection. Okay, so let's dive into really what are the difference between a prominence, a solar flare, and a coronal mass ejection. So if we talk about a prominence is the loop of relatively cool magma, for lack of a better term, incandescent gas that extends above the photosphere. So when that explosion occurred, it created a loop or an arc of gas in the atmosphere of the sun. Arc blowing of gas caused by a disturbance in the sun's atmosphere. This bends backwards into the sun, and that's what we were seeing, these arcs that go backwards, and that gravity from the sun pulls that material back into Earth, or back into the sun. It follows lines of magnetic force. So when it explodes, it finds the magnetic field and lines itself up with the magnetic force of the sun. And this may last for several weeks. We may see a huge loop for a long period of time. Now, we can't witness it from the sun. We should never look at the sun without glasses or a filter on, but we would never be able to see it with our bare eye, even with a filter on. We have to get telescopes, we have to get cameras that get zoom way in to see that prominence. So here's an example. Here's the sun, right? And here is a looped arc of gas, right? Look at the size, the approximate size of Earth. Look at how massive that thing is. Huge explosion outward from the sun. Here's another one. Here's the sun, right? Here's a huge arcing, right? And it comes way down and comes back around. There's Earth. All of us, right here, tiny little piece. And then here's another one. I'm not sure if you can see it that well, but you can see the arc right here goes either one direction or the other. And that lines, the gases from the sun line up in the magnetic field of the sun.
Okay, so for the next type of disturbance is the most violent disturbance. It's called a solar flare. You've probably heard that in the news, but it is the most violent of solar disturbances, and it's this explosion of energy that comes from the sun that's associated with magnetic disturbances on the sun's surface. So we talked about the sun being very active in these sunspots. Well, these sunspots, when they have these huge explosions and you see these very large prominences, well, a solar flare is blown outwards in the direction of that explosion as well. We don't necessarily understand what triggers them specifically, but the temperatures can reach over 20 million degrees Celsius, right? Compare that to something that we can wrap our head around. We've all held a match or lit a lighter. That flame can burn you in an instant, and that is less than 2,000 degrees Celsius. We're talking about 20 million degrees Celsius. That's pretty crazy. Can travel upwards thousands of kilometers within minutes and usually lasts less than an hour. Right? So this explosion can be very huge, thousands of kilometers per minute, right? And lasts less than an hour. And usually we see a sunspot is where this typically, this activity is found. So the last thing that we need to talk about as far as disturbances, what's called a coronal mass ejection, or CMEs. Okay, this is part of the coronal, or the outer shell of the sun, that's thrown into the space from the sun. Disturbances of the atmosphere, or the corona, that can affect Earth's magnetic field. Now, when these explosions occur, right, it sends these waves, this coronal mass ejection sends waves that cause geomagnetic storms. Okay, and geomagnetic storms affect anything that really uses electricity, but a lot of things that use signals from the satellites and whatnot. So when those storms hit those satellites, it affects things like radio and satellite communication. It can cause blackouts and other problems on Earth. We are so dependent on electricity that if a huge eruption on the sun happened, it could be pretty detrimental to us pretty quickly. Once that storm hit Earth, it could be pretty detrimental. Lastly, okay, now everything that we've talked about so far has been just a momentary eruption. Solar winds are something that have been occurring ever since the sun has been created. Solar winds have been occurring, right? So this is a continuous stream of high energy that leaves the sun. It's electrically charged particles called ions from the corona that are pushed into space in all directions at all times forever, right? Well, how do we know this, and what does it happen? What causes do we see on Earth? Well, the first thing is that it causes auroras, right? And in the northern hemisphere, they're called aurora borealis, or northern lights, and in the southern hemisphere, they're called aurora australis, or southern lights, right? They can cause these auroras, and we'll talk about those in a second. And they can affect any and all electronic devices in space, like satellites, radios, cell phones, including astronaut gear. So if you have astronauts in space and these solar winds hit them, it can affect their instruments and gadgets that they're using and whatnot. So they have to be mindful and careful of that as well. Let's take a look at these solar winds. So here's an image, not to scale, but here's the sun, here is Earth, and these blue lines represent these solar winds. So you can see that the purple lines, these purple lines represent our magnetic field and our magnetic shield around Earth. Without the magnetic field, Earth's atmosphere would have burned up very quickly in Earth's history, right? And we never would have lived. We never would have survived. No life on Earth would survive. It would be too hot and too arid of a atmosphere. There would be no atmosphere to survive. So this magnetic field gives us lots of protection, and you can see that when the solar winds hit this magnetic field, they're deflected to the poles, right, the north and the south pole. If we think of Earth like a magnet, there's a north pole and a south pole, and then that's where they enter our magnetic field, is at the poles. Okay, well, while they're entering, they have to go through our atmosphere, and when they go through our atmosphere, they cause auroras. The electrically charged particles interact with the oxygen and the nitrogen in the air, and they cause these very bright greens and reds and oranges, very beautiful colors. But they only really happen at the poles. It's only with really strong solar winds where we might see closer to the equator where we could see solar auroras. Speaking of auroras, let's get through it real quick. Sheets of lights that are produced by high energy particles that are released from solar winds. They react, we talked about this, oxygen and nitrogen are what they react with in the upper atmosphere. As the electrically charged particles are entering our magnetic field, they interact with the oxygen and the nitrogen. Usually seen in the night sky by Earth's magnetic poles, but strong storms, extreme geomagnetic storms, we could see closer to the equator. Here in lower Michigan, there have been chances for us to see auroras, but very few chances. Northern Michigan, into Canada, Alaska, all of those areas see lots of solar winds often. When high energy particles hit oxygen, we see green colors. When low energy particles hit oxygen, we see a red color, and the northern and southern lights. Let's take a look. Right, here's an image of these high or low energy. High energy particles, right, because it's a green curtain coming across. And then let's see if we can pull up. This video shows you aurora over the series of a night, right? And I'm not going to show you the whole thing, but as we move throughout the night, we see huge curtains of these greens and beautiful colors. And we've got some dramatic music that goes along with this. It's on my bucket list to see the Northern Lights. I hope you put it on yours, because to see a sight like this would be absolutely mind-blowing. Video 3 down! Check whether you watched it or not. Peace out, homies.